Let's take a look at some important logical equivalences. So let's first take a look at implication and its contrapositive. And we want to show that implication, P implies Q, is equivalent to its contrapositive. Not Q implies not P. And so in this truth table below, I've already listed every possible combination of truth values that we can assign to the atomic propositions P and Q. And next to that, what those would be in terms of the negation of those propositions. So let's fill in the rest of the truth table for implication and contrapositive. In the first row, we see that P is true and Q is true. And so that implication, P implies Q, is true. In row 2, we see that P is true and Q is false. And so now we have a problem. Implication doesn't hold. Compound proposition is false if P is true and Q is false. In rows 3 and 4, we see that P is false. And when P is false, implication tells us nothing. It says we don't know anything about the truth value of Q. And so in those situations, P implies Q is always true. All right, let's take a look then at the contrapositive. Not Q implies not P. Again, for this one, the times that we care, if not Q is false, it's always going to hold. However, we do care when we're moving from true. So in the case where we're moving from not Q being true, we need not P to also be true. So in row 4, we see that not Q is true and not P is true. So this works. But in row 2, we have a situation where not Q is true and not P is false. And that can't hold because this implication, not Q implies not P, that means that if not Q is true, then not P must also be true. And this breaks it. And so this becomes false. And we see these truth tables are in alignment. True, true, false, false, true, 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 true. And so those are equivalent. Another really important set of equivalencies is De Morgan's laws. And this comes out in the following way. If we want to negate a conjunction, such as the following, the negation of P and Q, De Morgan has told us that we can break that down, and what it looks like is not P or not Q. So it's taking that out of that parentheses, breaking that conjunction apart. And what's really important to note is that when we do so, the negation goes to each of its component variables, but then that and becomes an or. And then the second of De Morgan's laws is how we negate disjunction, P or Q. And what happens in this case is that, again, we take the negation and we apply it to each of its component parts, but then when we combine them together, that or becomes an and. So let's take a look at what that looks like in terms of application. Let's take a look at an example of De Morgan's laws applied to statements in plain English. So we're going to try to find the negation of each of the following. Okay, we'll start off with a simple sentence. Eric bicycles or runs. And we can break that down into Eric bicycles as one atomic proposition and Eric runs as a second proposition, and we see that's an or in the middle. And so if we want to negate that, we can apply De Morgan's laws. Not the disjunction P or Q is equivalent to not P and not Q. So if we write that out in plain English, what we see is Eric does not bicycle, so that is our not P, and he does not run, and that's our not Q. Okay, let's do the same when we have an and in the middle, and we can see that we've got an and. And we'll break this sentence, Angela works in Ottawa and Toronto, down to Angela works in Ottawa and Angela works in Toronto. So that would be true if I work in both Ottawa and Toronto. So if I want to negate that, assume that's not the case, then the negation of that conjunction P and Q, we can break down by De Morgan's laws. And he says that is equivalent to not P or not Q. Well, not P is just Angela does not work in Ottawa. Not Q is Angela does not work in Toronto. And so combining those with that or, we get the sentence, Angela does not work in Ottawa, or, so that's our not P, or she does not work in Toronto. There's our not Q. And that's an application of De Morgan's laws. There are certainly other equivalences. We could look at the equivalence of distribution of and over or. And the way that we do that is we could apply a truth table and show you that these values are equivalent. And so you can see here, these can be found in the last two columns. So to get there, we have to break down every possible combination of P, Q, and R, the truth values that those atomic propositions could take on. And that's going to take 8 rows. So let's just quickly go through this example. So first, let's find the times that Q or R is true. And we know that we only have to consider then these columns of our table. And Q or R is true as long as one of Q or R is true, has a truth value true. So there's only a few times where it does not, right? And that is when they're both false, this value will be false. But the rest of the time, Q or R will be true. So I'll skip those rows because those are the only 2 times that this is false. And so to make sure we can see that, we'll just fill that out in red. Those are the times where we have a value of Q or R that is false. So now we can move our attention to the right side of this equivalency. And we'll first start by looking at P and Q. And P and Q is only true if both P and Q are true. So this only happens a handful of times. We can look at the first row, true, true. Both P and Q are true, and so P and Q is true. In the second row, we have true, true as well, and so P and Q is also true. But in every other instance, there's at least one of P or Q is false, and so that conjunction P and Q must be false. So we can fill in the remaining rows. Finally, we can turn our attention to the last piece of that puzzle, which is P and R. And then we'll have all of the components that we need to determine the truth values of our logical equivalencies here. So now we have P and R, and we know that that's only true when the truth values of P and R are both true. So we can find that in rows 1 and row 3. And the rest of the time, at least one of the 2 has a false truth value. So I know that I'm going to put true here and false everywhere else. Now we have all the information that we need to determine P and Q or R, and the right side as well. So first we'll look at P and that disjunction Q or R. Okay, so this is only true if both P and the disjunction Q or R is true. And we can see that this is going to happen in a few locations. So it's going to happen in the first 3 rows. We see Q or R is true and P is true. Everywhere else, at least one of those combinations is false. And so we can fill in our table, true for the first 3 rows, false for the remaining. So the last piece of the puzzle is this right-hand side, and that is a look at P and Q versus P and R. And what we want is the disjunction of those 2 values. So these columns with an or between. And those are going to be true. That whole side is going to be true if either P and Q is true or P and R is true. And what we can identify is that this is only going to happen in those first 3 rows. After that, both P and R and P and Q are all false. And so again, only those first 3 rows are true and the remainder are false. And this is the definition of an equivalency, right? That the truth values in each row of that truth table are going to match. And so this is an equivalency. So I'll leave it as an exercise to fill in the truth table in the distribution of disjunction over conjunction. But we can take as fact that this also distributes. So if we have P or that conjunction Q and R, we can say that this is equivalent to P or Q and P or R. We will take a closer look at mutual implication. So we've stated in the past that P if and only if Q is the same as saying P implies Q and Q implies P. And so this piece here is the same as P if and only if Q. And we can show that that's true pretty quickly. So we know that P implies Q is true every time that if P is true, Q must also be true. And so in the first row, that holds. In the second row, it does not. This is false. And finally, for the remaining rows, it holds. And that's because despite the fact that P is false, there's no ramification to that implication P implies Q. So it's not a situation where P is true and Q is false. Our implication holds. Let's look at going the other direction. So if I'm going from Q to P, that means every time that Q is true, I want P to be true. And that holds in the first row, but it doesn't in the third. And so this is a time where Q implies P is false. When Q is false, this implication holds. It's okay. There's no statement about the truth value of P. And so here we have true, true. So when we combine the two together, so we've got P implies Q and Q implies P, that will only be true if this is true and Q implies P is also true. And we can see that this only happens in the first row and the last row. So here it is true. And in the middle 2 rows, it is false. And so the if and only if only holds, if we look at the right-hand side of the equation, we know that this only holds when both P and Q have the same truth values. And if we look at our truth values of P and Q, they're the same only in those first and last rows. And this shows that mutual implication, P implies Q and Q implies P, is equivalent to saying P if and only if Q. Both P and Q have the same truth values. There are many other logically equivalent statements, and we'll just list a few. The identity laws. If we have P and something that's true, that's equivalent to just saying P. And if we have P or something that is false, that's equivalent to P, because only one of that disjunction P or false must be true. So because false is not the one, we're just left with P. Domination laws. If we have a disjunction where one of them is true, because we only need one to be true, we don't even have to care about P. P or something true is always true. And P and something false, because we need them both to be true for that conjunction to hold, this is always false. We also have idempotent laws. So if we have either the disjunction or the conjunction, P or P and P, because they have the same value, we can just say that's equivalent to P on its own. And the double negation laws. If I have not P, that's the same as P. They're equivalent. We also have commutative laws. P and Q is the same as Q and P. And P or Q is the same as Q or P. The order there doesn't matter. The associative laws. So if I have P and Q and R, the parentheses in this situation, the brackets don't make a difference, because and they both need to be true. So the fact that the pieces in the middle also both have to be true means where I place those brackets doesn't matter. So as long as we're dealing with all ands or all ors, I can associate those groupings in any way that makes me happy. P or Q or R is the same as P or Q or R. And then I have absorption laws. So if I have a situation where I've got P or a conjunction that involves P, so it's important that P is in there, then what I'm saying on the right-hand side, if I have P or P and Q, for this to be true, P has got to be true. And so if the right-hand side is the piece that makes this disjunction true, then P is true. If the left-hand side is the piece that makes this disjunction P or P and Q true, then P would have had to have been true. So no matter what, for this to work, P must be the case. And so P is the thing that makes this true. So this is the same as saying this is equivalent to P. We can do the same with the second of these absorption laws. And the final piece are negation laws. P or not P, that's always true. One of them is true. If P isn't true, then not P is true, and vice versa. And finally, P and not P both can't be true at the same time. So these are negation laws. You'll have a list of these available to you. And that wraps up our piece on propositional logic.
This was fun, but I really like the logic games at the beginning.
Okay. Do you want to play another one? Maybe one from the Island of Knights and Knaves?
Yes, I've got one.
Okay, let's you and I play the parts.
At least one of us is a knave.
I have nothing to add. If you can solve this and decide which of Eliana and I are the knight or the knave, or the combination of the two, add a message to Teams.
Thanks for watching.
See you next time when we explore predicate logic.